So we need to be able to fluidly move between degrees and radians, and they are the formulas, if you like, that we use to convert between the two. I'm not going to re-prosecute the case as to why this works. If you don't know and you need to know, then let me know and I will talk to you about it. But that's effectively the conversion here that we have covered in some depth in methods 3. And here are two simple examples. I just want to spend a moment to say that although, look for shortcuts where you can. So 135 degrees, for example, it might not be apparent straight away, but 135 degrees can be broken down to a 90 plus a 45. So when it can be broken down to some really common angles like 90 and 45, 300, 60 and 30 into multiples of them or combinations of them, use that because there are certain angles that you need to know pretty much off by heart. Even though they're on your information sheet, you need to be able to recognize them as you go along. So just a reminder from last year then, the angles that you should be able to recognize are, apart from things like zero, just zero obviously, but you should be able to recognize pi on 6, which is 30 degrees, pi on 4, which is 45 degrees, pi on 3, which is 60 degrees. They're the fundamental acute angles. And then you've got pi on 2, which is 90 degrees, pi, which is 180 degrees, 3 pi on 2, 1.5 pi's, which is 270 degrees, and 2 pi, which is equal to 360 degrees, and then more rotations beyond that. But basically, those ones in red there, I want you to get to the point, whatever you need to do, write them. If you don't know them yet, write them down somewhere. You use a flashcard app on your phone, write them on the back of the toilet wall, or whatever you need to do to just get it so that you remember them all, please, because they are so common. If you don't have to refer to your information sheet every single darn time you see it, the better it is for you. Okay, so they're the really common ones. I tend to just kind of remember that these two are complementary, like the 30 and 60 make up 90 degrees. So the 4 is 45, the 6 goes to 30, and the 3 goes to 60, kind of that reverse kind of thinking. So that's how I kind of remember those ones. And then these ones I just tend to remember because they're pretty, well, to me, they're pretty obvious right angle measurements, I suppose. So yeah, make sure you know those ones. Because if you do, then instead of going to 135 degrees equals and doing all this kind of stuff, you can literally go like I did here, or you can go, oh, that's 3 lots of 45 degrees. So that's 3 lots of pi on 4, which is 3 pi on 4. PS, the other thing which I find students shouldn't have to struggle with, but unfortunately you do, is the fact that radians are often a fraction measurement, like pi on 4, that kind of thing. If you're weak on your fractions, do something about it. I'm happy to help anyone. Like, I'm happy to throw video resources at you. I'm happy to have one-on-one tutorials in your own time. Whatever it is, you must be able to utilize fractions without freaking out. You just have to. So be on it. Do something about it if you're not. And here's just a simple example of converting into degrees from radians. Again, the half does not have a radian, does not have a degrees symbol on it, so it's definitely a radians measurement, and so therefore you can convert it, and that's an exact conversion there to 90 on pi degrees. There's my suggestions there. If you were in my class last year, you've heard this already, and that is you are allowed to take more than one calculator into your exam and into tests. I would take your scientific calculator in and put it into degrees. I would take your graphics display calculator in and keep it in radians. And then it's a matter of remembering which calculator to pick up. See what I mean? Rather than accidentally getting halfway through a calculation before you realize your GDC was in the wrong measurement to start with. However, at least on the blue calculators, the ones with blue borders, it is fairly easy to change between degrees and radians. You literally just go click, click to convert between them. If you've got the old calculator, so pre-blue, you have to click on the battery icon, go to document settings, convert it to whatever you want to there, and then click on make default if you want all of your documents to be like that, or click on OK. to change it. So it's a bit faster on the blue calculators. I still think there's some merit, though, in actually just doing degrees on your scientific calculator and doing radians in your graphics display calculator. All right, before I move on to the next one, I'm just trying to blast through this. Does anyone have any questions? Otherwise, I'm going to assume you're okay. Here we go, unit circle. So just to remind you, and I'm going to draw some really important points because you need to be across this. The reason for the unit circle is so that we can extend our definition of sine, cosine, and tan beyond 90 degrees. Our fundamental definition of sine, cosine, and tan is from a right angle triangle. It's a ratio of sides. So we've got, if this is my angle here, theta, then I've got an angle that is, a side that is opposite that angle. I have a side that is next to, but not the hypotenuse. We call that adjacent. And then we've got the hypotenuse itself. And so we know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. And that's pretty much every single combination of side there. Okay, so that's what the basic definition is. But of course, a triangle, a right angle triangle, is limited, or all triangles are limited that all angles have to add up to 180 degrees. And in a right angle triangle, half of that's taken up by the right angle, which means that these two angles are always going to be less than 90 degrees. So that means that sine, cosine, and tan is limited to 90 degrees, or pi on 2. I think I might start talking in radians instead of degrees right now to make it to get you used to that sort of way of talking. So what we do instead in the unit circle is we say, well, I could talk about the angle being here. It will be that angle there, or it could be there. Always taken counterclockwise, always taken from the x-axis, the positive x-axis. Or I could talk about an angle being there, or I could talk about an angle being not just there, but there. So the unit circle allows me to create lots of different angles of lots of different sizes. And all we have to do is convert the placement of that line, that angle line, to something else. So let's stick with quadrant 1 just so that we can get it right. In quadrant 1, if I draw a line here, I have an angle theta, which is an acute angle. Remember, acute means between 0 and 90. It's called the unit circle because we make the line arbitrarily 1 unit long because it makes everything else more interesting, I suppose. If I then talk about, and this is the key thing, if you don't get this, keep asking questions till you do. If I talk about the coordinates of that point there, I don't know what it is, but it's going to have an x coordinate and it's going to have a y coordinate. Whatever that is, it's going to be an x coordinate and a y coordinate. That x and y coordinate will change depending on the value of theta. We okay so far? This is supposed to be a reminder, so just tell me if you're struggling with that. If we convert that onto our right angle triangle, we would have a hypotenuse of 1. We would have a opposite angle, or opposite side, of y, and we would have an adjacent side of length x. Again, if this is the x coordinate, that means it's x units away from the origin. So that distance there will be the same as that distance there. It's the x coordinate. The y coordinate is how far in a vertical direction I am away from the origin. So if the origin is here, then the y coordinate is all the way up here. So it's all the way up here. So the length between the x-axis and that point there has got to be length y, and the length between the origin and along the x-axis to this point here has got to be x. Good with that? This is so important. You must think of sine, cosine, and tan in terms of coordinates on the unit circle. So sine theta in our diagram is simply equal to opposite over hypotenuse, which is what we chose to be 1. So in other words, it ends up being the y coordinate. Cosine of theta is equal to adjacent over the hypotenuse, which is simply the x coordinate when it's the unit circle. And this is why we're choosing that length to be 1. So the x and y, so it's just the simple x and y coordinate. And tan of theta, which is opposite over adjacent, would therefore be y over x. Okay? Which is, by the way, I mean, I would just leave it as y over x, but that is effectively the gradient of that line. So tan can be considered the gradient in the unit circle. Sine is the y coordinate and cosine is the x coordinate. Okay with that so far? Sorry, Tian? There's only one in the unit circle. There's only one line. Yes, so the hypotenuse line. Yep. Okay, good question. Thank you. Alrighty. Other quadrants then. If we have theta being all the way in the second quadrant, e.g., then the coordinates here are going to be, and I'm just sort of going to do it this way. It doesn't really kind of make sense in how we really talk about things, but the x coordinate is going to be negative and the y coordinate is going to be positive, okay? Which means that sine is going to be positive because the y coordinate is positive. Cosine is going to be negative because the x coordinate is negative. And tan is going to be negative. You can see it. The slope of that line is negative, right? Plus also rise over run, y over negative x. By the way, that's why we can call tan the gradient, because it's rise over run from the origin. The gradient is y over negative x, and so it's going to be negative some sort of value. Okay, so that's the coordinate. The way we piece this together is that if theta goes from 0 to here, then what we're left with here is the supplementary angle, theta hat. Okay, theta hat. It's the angle I get when I subtract theta away from 180. So what we have in this left-hand side triangle is we have an acute angle triangle, and therefore we can use theta hat is opposite over sine of theta hat, is going to be opposite, which is going to be y over 1. Cosine of theta hat is going to be adjacent, negative x over 1. And tan is going to be y over negative x. Okay? So the coordinate here is worked out from theta hat. So theta hat is called the reference angle. I say theta because that's what I'm doing, but I want to make sure that we're really clear here that it could have been, I could have used x or beta or gamma or g. It's just a variable. So whatever the variable is of the angle, it's going to be that hat. So if this was an angle x, then that would be x hat, etc. It's called the reference angle because it's the angle that it's the acute angle that we use to find the x and y coordinates. Okay? It's always the angle between the x-axis and the unit line. It's never between the vertical axis, always between the horizontal axis and the line. Okay, we good with that? Again, this is a review from last year, but I think it's an important one. Okay, so what does this mean then? It means that sine theta is going to be effectively the y coordinate. I'm actually going to write y coordinate instead of y, so I'm not confusing it with the negative x comma y that I've got there, is the y coordinate. And the y coordinate is going to be the sine of theta hat. Okay? So we have got sine of theta hat, like so. Actually, I'll even put it onto this diagram here so that you can see it. The x coordinate is going to be negative cos theta hat, and the y coordinate is going to be sine theta hat, like so. That's the x and y coordinate. Okay, so the cos theta is going to be the x coordinate. I'm conscious of time, so I'm wrapping up here. It's going to be the x coordinate, and because it's in the second quadrant where it's negative, that's going to be negative cos theta hat. And tan theta is effectively going to be y over x, which is going to be sine theta hat over negative cos theta hat. That's going to be negative sine theta hat cos theta hat, like so. We can put that negative outside. So those are how we get to the next quadrant of the next quadrant. And effectively, we've now extended our definition from just angles between 0 and 90 to now angles between 0 and 180 to 0 to pi, okay? Where we're headed next is having a quick look at the other quadrants as well, like so, and then we'll have a look at some examples. So I haven't quite got as far as I was hoping to. So rather than giving you video homework, I'm actually going to just say no homework tonight, and we'll work harder in our lesson tomorrow to make sure that we're across all this detail.